Hello dear students, welcome to BYJU'S Exam Prep. Now under this Concept Capsule series, we take up the following concept called Catalan number from discrete mathematics. We also find this Catalan number under algorithms even in data structures. Before starting the concept, this is about me, myself Sridhar Dhulipala. I am having 20 plus years of teaching experience and my qualifications are MTech Saka from NIT Karnataka Surathkal and MSc Mathematics from JNTU Hyderabad. And these are all my areas of expertise, my dear friends. Okay. So now let us start with Catalan number. See, Catalan numbers are sequence of natural numbers which are solutions for many counting problems. There are many counting problems for which Catalan number is the solution. Okay. Now, the nth Catalan number is given in terms of binomial coefficients. You all know binomial coefficients, NCR we generally use. NCR, the other way of representing it is NR. Okay. We can express this nth Catalan number in terms of this binomial coefficient and that formula is given by this one. Cn is equal to 1 by n plus 1, 2n Cn. Here 2n n is same as your 2n Cn, my dear friends. If you expand it, you are going to get the other form of the same Catalan number. Actually, this Catalan number can also be expressed in terms of this product. What is this product? N plus 2 by 2 because you have to put k is equal to 2 to n. So when you put k is equal to 2, it is n plus 2 by 2. If you put k is equal to 3, it is n plus 3 by 3. And continuing this way, if you put k is equal to n, it is n plus n by n. If you actually simplify this, see if you observe numerator going from n plus 2 to 2n, what you do is you multiply and divide by n plus 1 factorial. So that the numerator becomes 2n factorial. Because you divided with n plus 1 factorial, that n plus 1 factorial will be there. And you see this 2 into 2, 3 up to n is nothing but n factorial, which is nothing but the same form. Okay, so there are different ways of expressing Catalan number, my dear friends. And actually, we use more often this particular formulation. That is Cn is equal to 1 by n plus 1, 2n Cn. That is whenever you say Catalan number, you try to remember this formula. 1 by n plus 1, 1 by n plus 1 into 2n Cn. Actually, Catalan number is solution of the following recurrence relation. There is a recurrence relation for which Catalan number is solution. And the base condition for this recurrence relation is C0. C0 which is equal to 1. So this is the recurrence relation, my dear friends, for Catalan number. That is, Catalan number is solution of this recurrence relation. Actually, there are many problems for which Catalan number is the solution. What actually happens is, whenever the problem is given, we try the recurrence relation. And that recurrence relation turns out to be the following one, and for which Catalan number is solution. For this, Catalan number is solution. Hope you understand. So let us take up some interesting problems. And before that, let us see the sequence of Catalan numbers. C0, this is a base condition, which is 1. C1 is equal to 1. If you want, you can use the formula, sir. Cn is equal to what? 1 by n plus 1, 2n Cn. So if you want C1, which is 1 by 2, 2 into 1, that is 2C1, which is nothing but 1. And C2, what is C2? 1 by 3, 4C2. 4C2 is 6, 6 by 3 is nothing but 2. Using the formula, you can get it, or at least you can remember starting 5, 6 Catalan numbers, my dear friends. C3 is 5, C4 is 14, and C5 is 42. If you want, you can get it by formula also. C5 means what, sir? 1 by n plus 1, that is 1 by 6, 2n. 2 5 is 10, C5. Simplify this, you get this particular answer. Am I clear? So this is about the sequence, first few Catalan numbers or sequence of Catalan numbers. Got it? Now let us take up some problems for which Catalan number is the solution. The first problem is balanced parenthesis problem. Suppose we have n pairs of parentheses. Pairs, see, always parenthesis comes in pairs. Okay, so we are having n pairs of parentheses and you'd like to form a valid group of them. You want to form a valid group of them. Where valid means what, sir? For each open parenthesis, there should be an associated closed parenthesis. So whenever there is an open parenthesis, we should find an associated closed parenthesis. Then we call it as a valid parenthesization. Okay. So let us take one simple example. Now if you observe this particular example, is it valid or not? Let us check. See, this is open. For this, there is a closed one. This is open, there is a closed one. This is open parenthesis, there is a closed one. Am I clear? So for every open parenthesis, there is a associated closed parenthesis. Therefore, it is a valid parenthesization. Now what about this? Now this is open. For this, if you take this as closed one, fine. Now this is open. For this, if you take this as closed one. Now for this, no. So this is not valid, my dear friends. This is not valid. Of course, people use this idea also. Whenever the left parenthesis comes, they put +1, and whenever right parenthesis comes, they get -1. So ultimately, what you should get, +1 -1 means 0 we should get. Like that also you can verify. Am I clear? Now, the number of balanced parenthesis expressions using n pairs of parentheses. Suppose if you are having n pairs of parentheses, how many valid parenthesized expressions are possible? And that is given by Catalan number, my dear friends. So for example, when you are having only one pair of parentheses, so number of valid parenthesized expressions, this is the only one which is possible. Because C1 is 1. When n is equal to 2, C2 is equal to what? 2. See, you are having two pairs. See, this is one pair. So you can write this order or you can write this order. That is parenthesis within the parenthesis. The parentheses are within the parenthesis. N is equal to 3. What about this, my dear friends? C3. C3 is equal to what? 5. So if you want to know how many, directly you can use Catalan number. But if you want to know, you have to write it. Of course, generally they'll ask you what is this answer. They'll not ask you to write down all those valid parenthesized expressions. That is for your understanding. I am giving you that particular example. Hope you understand. Next one, multiplication orderings. And this particular multiplication orderings is useful when you do your matrix chain multiplication problem in algorithms course under dynamic programming. Suppose we are having a set of n plus 1 numbers. Here number of numbers are n plus 1, not n plus 1 numbers to multiply together. So you want to multiply n plus 1 numbers together. Meaning that there are n multiplications possible. See, if you are having two numbers, how many multiplications possible, sir? One multiplication possible. If you are having three numbers, how many multiplications are possible? 1, 2 multiplications. Okay. So if you are having n plus 1 numbers, how many multiplications are possible? N multiplications are possible. But the question is, how many multiplication orders are possible? Means here you are doing two multiplications. Whether you do this first followed by this, or you do this multiplication first followed by this. That is called multiplication orderings. So if you are having n plus 1 numbers, how many multiplication orderings are possible? How many multiplication orderings are possible? The number of orders, that is multiplication orders, without changing the order of numbers. We are not changing the order of numbers, sir. Numbers will be same at their place only. A, B, C means A first, B second, C third only. But the number of multiplication orders possible to multiply n plus 1 numbers is given by the formula Cn. If you are having n plus 1 numbers, the formula is Cn. Number of numbers are n plus 1, then the formula is Cn. Remember that. Example. So we are having two numbers. Multiplication orderings possible is C1. Two numbers are there. So n plus 1 is 2. Here n plus 1 is 2. So what is n? So number of multiplication orderings possible is C1, which is 1. And when you are having three numbers, because n plus 1 is number of numbers, therefore number of multiplication orderings possible is C2. C2 is 2. You all know that, right? Either first you can multiply AB, the result can be multiplied with C, or first you can multiply BC, the result can be multiplied with A. Suppose you are having four numbers. That is n plus 1 is equal to 4. That is n is equal to 3. So number of multiplication orderings possible for 4 numbers is given by C3. C3 is what? 5. And these are the multiplication orderings. And you can also replace these numbers with matrices, my dear friends. Number of multiplication orderings possible for multiplying n plus 1 matrices together. You can convert that problem. This problem can be converted to multiplication of matrices problem also. But you have to keep the compatibility of the matrices or conformability of the matrices into mind. Okay, you should keep that in mind, that whether the product is conformable or not, because you cannot multiply any two matrices, my dear friend. So if you are writing A1, A2, A3, these two, that is, the orders of the matrices must be in such a way that the multiplication is possible. We call it as conformability for multiplication. Am I clear? Please remember that. Except for that, the idea is exactly same. Got it? The next one, binary trees. What is a binary tree, my dear friends? There is a designated node called root, and the remaining nodes are partitioned into two binary trees called as left subtree and right subtree. Got? Now, the number of binary trees, please see this carefully, number of binary trees with n unlabeled vertices. N unlabeled vertices. With labelings, the story may be different, but with unlabeled vertices is given by Catalan number. Number of binary trees with n vertices, people say, but please be careful, it is n unlabeled vertices. Am I clear? With n unlabeled vertices is given by Catalan number, which is Cn. Got it? For example, if you are having only one vertex or one node, how many binary trees are possible? This is the only binary tree, because C1. C1 is 1. Number of binary tree with two nodes. So according to the formula, C2. C2 is equal to what? 2. And this is 1, and the second one is this. These are the two binary trees with two nodes. Labels are not given, my dear friends, because labels are given, AB, BA will be different. Please be careful. Am I clear? That's why unlabeled vertices. Next, n is equal to 3. So what is the answer? C3. 5 binary trees are possible with 5 unlabeled vertices or unlabeled nodes. This is one, second one, third one, fourth one, and fifth one. These are the binary trees with 3 unlabeled nodes or vertices. Got it? Next comes strict binary tree. Of course, the terminology may vary, my dear friends. Here, strict binary tree means each node is having exactly 2 children or 0 children. Each node is having either exactly 2 children or 0 children. We are calling it as a strict binary tree. Am I clear? Sometimes some people may use different terminology for this. Okay, please remember. Strict here means each node has either degree 0 or 2. Degree of node is 0 or 2 for every node. Okay, then we call it as a strict binary tree. Now, see this carefully. The number of strict binary trees with n unlabeled vertices is given by Catalan number. See the formula here, C n minus 1 by 2, not Cn, it is C n minus 1 by 2. If you are having n nodes and if it is a strict binary tree, the number of strict binary trees with n unlabeled vertices is given by formula C n minus 1 by 2. Or if you want to say in terms of n, but that n will be internal nodes, not number of nodes. N internal nodes, if you know, that is given by Cn, sir. With n internal nodes, the answer is Cn. Okay, let us try to understand this. Look at this example. N is equal to 1. So, n is equal to 1 is the number of nodes if you take it. Then number of strict binary trees possible will be Cn minus 1 by 2. That is C0. C0 is what, sir? 1. And that is the only one. Am I clear? That is a strict binary tree because degree of this node is 0. N is equal to 3. Okay. So, it is C3 minus 1 by 2, which is nothing but C1. C1 is what, sir? 1. With 3 nodes, there is only one strict binary tree. That is this one. Okay. Which is C1, which is equal to 1. Am I clear? And with 5 nodes, you have to write C5 minus 1 by 2, that is C4 by 2, that is C2. C2 is what, sir? 2. And these are the two strict binary trees, my dear friends. C2 is equal to 2. Now, if you say the same thing in terms of internal nodes, here how many internal nodes are there? No internal nodes. So, number of internal nodes, 0. Then number of strict binary trees with 0 internal nodes is given by C0. C0 is 1. Here 0 is internal nodes. Here how many internal nodes are there? Only one internal nodes. Only one internal nodes. Am I clear? Therefore, with one internal node, what is the answer? C1. Here how many internal nodes? 1, 2 and 1, 2. 2 internal nodes. With 2 internal nodes, how many strict binary trees are possible? 2. So either you can say in terms of internal nodes or you can say in terms of number of nodes, my dear friends. Am I clear? The last one. Let us consider the last problem, that is stack permutation. That is, suppose if I give you a sequence of numbers using a stack, what are the different permutations you can obtain for those sequence of numbers? For example, I'll give you the two numbers 1 and 2, or let me put this way because stack no, so let me put this 1, 2 are the two numbers and I am having a stack. Using a stack, you all know what is a stack? It is last in first out, LIFO structure. So here you can push 1 onto the stack, then you can pop 1 from the stack. So 1 is printed. Now again you can push 2 onto the stack and you can pop 2. So you can get this 1, 2 sequence from 1, 2. That is one sequence we can obtain from or obtain using the sequence 1, 2 using a stack. Suppose same 1, 2. The other way is you push 1, don't pop it now. Then you push 2 also. Now you pop the elements. So when you pop it, what are the elements? First 2 can be printed, then 1 can be printed. That is, you can get this permutation, sir. You can get 1, 2 permutation or 2, 1 permutation. Am I clear? But if I am having 3 numbers, 1, 2, 3. If I am having 3 numbers, 1, 2, 3, which stack permutation is not possible? See, can I get 1, 2, 3? Yes, I can push 1, pop it, push 2, pop it, push 3, pop it, I can get 1, 2, 3. Can I get, let us see what are possible permutations using 1, 2, 3 first of all. First of all, let us see what are the possible permutations, total possible permutations, let us see. 1, 2, 3, 1, 3, 2. I am not talking about stack permutation, total number of permutations. Using 3 numbers, 6 permutation, that is 3 factorial permutations are possible. I am just writing all of them. Out of that, which of the permutations we can get using stack? Let us see that. 1, 2, 3, 1, 3, 2. 2, 1, 3, 2, 3, 1. Next 3, 1, 2, 3, 2, 1. Now can you get 1, 2, 3 from this? How you can get 1, 2, 3, sir? Push 1, pop 1. Push 2, pop 2. Push 3, pop 3. This can be done. So first you can push 1, pop 1. Push 2, pop 2. Push 3, pop 3. So 1, 2, 3 can be obtained, no problem. 1, 2, 3 can be obtained. Next, this can be obtained. What about 1, 3, 2? See, using 1, 2, 3, you want to get 1, 3, 2. So 1, 3, 2 means what we can do is, you can first push 1. This is done. I am talking about second one. Push 1 and pop 1. Then you push 2, don't pop it. Then you push 3. Now pop the element. That is 3, you pop, then 2 you pop. Means what? You can get 1, 3, 2 also. Next, what about 2, 1, 3? Let us try. With using 1, 2, 3, you want to get 2, 1, 3. Let us see. 2, 1, 3 means what, sir? Till you get 2, you have to push everything. That is, you push 1 and you push 2. That is, 1 and 2 are pushed onto the stack. Now you want to get 2 first, na? So now you can pop 2. Again, next what you want? 1. 1 also you can pop. Now what you do is push 3 and pop 3. So 2, 1, 3 is also possible. 2, 1, 3 is also possible. This is possible. This is also possible. What about 2, 3, 1? Let us try again. 2, 3, 1. See, if you want to get 2, 3, 1 means till you get 2, you have to push everything. So you push 1, then you push 2, then you want 2. So first pop 2. So what you do? You got 2 now, you pop 2. Don't pop 1. Now what you do? You push 3. Because you want 3 now, pop 3. Now you pop 1. 2, 3, 1 is possible. 2, 3, 1 is possible. Let us try 3, 1, 2. Can you get 3, 1, 2? With 1, 2, 3, can you get 3, 1, 2, sir? First what you do? Push 1. That is, till you get 3, you have to push everything. So then you push 2. Then you push 3. Now what do you want to get? 3, 1, 2. So first you can pop 3 from this. But can you pop 1? After 3, can you pop 1? No. So this is the stack permutation. This is the permutation which is not possible using stack. So this is not a stack permutation. So except this, you can try this, sir. You can get this. So except this, remaining all are possible. So using 3 numbers, how many stack permutations are possible? 5 stack permutations are possible. But if you just ask the question, using 3 numbers, how many stack permutations are possible? You don't have to do all this work. You can simply say C3. What is C3? 5. Because the number of possible permutations of the elements 1 to n using the stack is given by Cn. We call it as number of stack permutations using n objects, which is given by Cn. Am I clear? So if you see, if you are having only one number of stack permutations possible is 1. If you are having two numbers, 1 and 2, number of stack permutations possible is 2. If you are having 3 numbers, number of stack permutations possible will be what, sir? C3, which is 5. What are they means? You have to do it. Actually, you say that 3, 1, 2 is the one which actually identified for a given permutation. To identify whether it is possible stack permutation or not, we use this 3, 1, 2, my dear friends. Suppose whenever you are having 1, 2, 3 as the numbers, if you want to get 3, 1, 2, it is never possible. It is never possible. Suppose if I am having A, B, C, C, A, B is not possible using stack. Okay, non-stackable permutation we call it. Am I clear? Please remember this. And suppose if I am having 1, 2, 3, 4, how many stack permutations are possible? That is given by C4. Okay, and what is the answer? 1 by 5. Okay, 8C4. You all remember what is the answer? 14, I think, right? 8765 by 5 into 4 factorial. Correct or not? 1 4 factorial cancel, 1 4 factorial will be there. 4 2s 8 cancel, 3 2s and this 5 cancel, 14 is the answer. So what is C4? 14 stack permutations are possible. 14 stack permutations are possible. And one interesting question is, please answer this. Of course, it is not a live one, so I'm just asking, keep this in mind and answer. 1, 4, 2, 3. Can you get this stack permutation or not? That is, using stack, can you get this permutation or not? Can you get this permutation using a stack? Now the simple logic is, see this carefully. You are having 2, 3, 4. This is also a sequence. Whenever you are having this, 4, 2, 3 is not possible. As I told you, ABC. Then CAB is not possible. This followed by this and followed by the middle one. This is never possible, remember, sir. So therefore, it is not possible stack permutations. And there are many problems for which Catalan number is the solution, my dear friends. And for all these problems, what actually happens is, for the given problem, we try to derive a recurrence relation. And that recurrence relation turns out to be the recurrence relation of the Catalan number, and whose solution is Catalan number. Am I clear? So this is about Catalan number, my dear friends. Thank you. Please subscribe to BYJU'S Exam Prep app to get more videos. Thank you.